Speaker is here, so we can start our session with the talk of Abdurakhmon Aliyev on the stochastic perturbation, central limit theorem for stochastic perturbation of the circle maps. Please.
Good evening, everybody, and thank you for letting me speak today. Let's share my screen. Just a moment. My name is Aliyev Abdurakhmon, and I am PhD student of Mathematical Institute named after Romanovsky. We investigate system of this form, and where F is a map one-dimensional space whose real line or unit circle or this interval into itself, and Cn sequence of real valued random variables, and sigma is parameter. This is classical model of dynamical systems. What?
Yeah. Let's continue. Yeah.
This is classical model of dynamical systems with noise, and this kind of systems have been investigated by a lot of science, but I want to give a little information of works which near my specialty. These authors considered in their works with this system where F is period doubling map on this interval into itself, and Cn identically independent identically distribution with Gaussian distribution. Then their main result in their papers using renormalization technique after appropriately rescaling space and time, the Lyapunov exponent at the transition satisfies some scaling relations. Next, Wood, Sinai, and Hanin also use this at work of Wood, Sinai, Hanin. F also period doubling function on I, this interval, and Cn is also identically independent identically distribution, but it's uniform distribution, mean minus epsilon and epsilon interval. They rigorous thermodynamic formalism approach for critical circle maps, these period doubling functions. Among many other results, these authors studied the effect of noise on ergodic properties of these maps, and showed that for systems with weak noise at the accumulation of period doubling, there is a stationary measure depending on the magnitude of the noise, which converges vanishing noise to the invariant measure of the attractor. The next work is the most important for us. Oliver Diaz Espinosa and Rafael de la Lave.
Excuse me. Can I ask you? You just mentioned the invariant measure of the attractor. What is it? What is the meaning of this invariant measure of the attractor?
Okay. If we see this function, a period doubling function, and if we see its iterations, I can draw some.
No problem. So you want to just consider a deterministic situation without noise, yeah?
Yes, without noise. Yes, without noise.
Yes. And then we can expect attractor. But what is invariant measure of the attractor? What does it mean?
Can I ask? Can I say about this one? So
Yes.
Wolf, Sinai, and Kanin they studied the Feigenbaum map, and then this map is with one. It is unimodal map, continuous map of the interval minus 1, 1, and with one maximum at the point 0. And then this map is a fixed point of renormalization operator for such maps. And this map has attractor of counter type. So we can say that this map on the interval minus 1, 1, but this attractor is such set which is which has 0 Lebesgue measure, and all orbits except periodic points tends to this set. So this set is called attractor of the Feigenbaum map, and then here there is the invariant measure which supported here, which sit on this counter type set, and then it is invariant measure of this set.
So this is invariant measure for initial map, yeah?
Yes, invariant measure of initial map G.
So
yes.
I know this, but it was a little bit strange written. Invariant measure of the attractor.
No. This, invariant measure of which seat, which
I understand.
Seat, yes.
Okay.
Yes.
Thank you very much.
The next work is Oliver Diaz-Espinosa and Rafael de la Lave studied in their work study stochastic perturbation of several systems which we remark this which satisfies which define these intervals or this space. Using renormalization group technique, among other, they proved a central limit theorem for critical cycle maps with golden mean rotation number and some mild condition on stochastic noise. Next, central limit theorem for one-dimensional dynamical systems with external noise. First, I'll give two basic theorems of Oliver Diaz-Espinosa and Rafael de la Lave, and I give examples that satisfy the condition of these theorems, because conditions of these theorems are seems complex. Then we will make the following assumptions. Let F second derivative smooth map and M real line or interval or unit cycle. If M interval, we will further assume that there is a number, a positive number, such that F is second derivative, second order smooth this interval, and image of this interval is subset this interval. Then let C and B sequence of independent random variables with P bigger than 2 finite moments. We will assume that mean of this sequence is equals 0 for all n, and for their sum for positive constants. Second, and P's means bounded from above and below. Next, let X belongs to M and sigma positive number fixed, and consider this system with initial point X. Then we also these xn bar sequence are called stochastic trajectory of x, and we also define a deterministic trajectory of x by this. Then for real line or unit cycle defines the xn bar process by this way, and when interval, we define process provided by this condition. Observe that if these points doesn't lie this interval, so we have that the events, these events is subset of also these events. Then we using by Chebyshev inequality, we get this inequality. We can see this from this inequality if sigma tends to 0, probability of Cn is also tends to 0.
But only for fixed n. If n grows to infinity, it can grow. It can grow to not to 0. Even this probability can go to the 1. Yeah.
Yeah, but what we consider when sigma is go to 0. We consider
I don't understand. Yes. By going by pushing sigma to 0, you can do this probability very small for fixed n. But when n tends to infinity, it can happen that this probability goes to 1. Yeah.
M. This M.
Small n.
Are you asking about this probability P of Cn?
Exactly.
Yes, here sigma, in fact, in our case, sigma depends on n and
I see. Okay.
to 0.
Yes. Okay. If it will depend on n, of course, we can control this probability. Yeah.
Next, we need some functions to introduce general results of them. Let's define Lyapunov functions. These and these are defined by following formulas. Next, the linearized effective noise is defined as by this formula. We show that stochastic process, omega n stochastic process by normalized xn random variables. Next, I formulate first theorem of Rafael de la Lave and Oliver Diaz Espinosa. Let f be second order derivative smooth map where real line or interval or unit cycle, and let Cn be a sequence of independent random variables with p bigger than 2 finite moments. Suppose that for some x, and there is an increasing sequence of positive integers nk such that satisfying this condition, this limit goes to 0. Then let sigma k be sequence of positive numbers, assume either of following two conditions, each one or each two. This limits or this limits goes to 0. Next, then there exists a sequence of events bk such that probability of bk tends to 1, and two processes defined by these and these converges in distribution to standard normal as k tends to infinity. If furthermore the sequence Cn is supported on a compact set, then we can choose for all k bk as omega. Next, for the rate of convergence to Gaussian in the theorem, these authors got following results. Let f and Cn be as in theorem 1 and as minimum p and 3. Assume that this condition as theorem 1 holds some x. If sigma k is a second positive number satisfying this condition, we have this inequality where a is depends on only x. This is analog of a very Hessian inequality. Conditions of this first theorem and second theorem seems very complex, and the natural question is that there exists in a system satisfying these conditions. Authors of these theorems give two examples, and we introduce their results. Next. Results for systems at the accumulation of period doubling. Consider analytic even maps f on the interval this -1, 1 into itself such that satisfying these three conditions. First, f at the point 0 is equal 1 and x derivative x times derivative fx negative than equal 0, and f has negative Schwarzen derivative. We can see the set of these functions satisfies conditions P1, P3 is called the set S unimodal map. We can see this function f0 is equal 1, and from the second condition we have f is increasing means 1 to 0 and decreasing 0 to 1, and I introduce why we need the second condition. Next, let's denote by lambda f equal f1 and bf f lambda f. This is ff0, and this is third iteration of 0. We will further assume that P4 and P5 conditions. The set of functions that satisfies P1, P5 is called the space of period doubling renormalizable functions. It follows from P4 that intervals E0 minus lambda f and lambda f and E1 interval don't overlap. And if f belongs to P, second iteration of f of x in E0 has a single point which is a maximum. This came from this P3. This came from P3 condition. To change of variables x to lambda x, replace E0 by E and the maximum by a minimum by a maximum. You can see this image. There is fx and there is ffx. If we see this interval, it's E0, and if we cut this image there, this is similar to this image, and we can go this function to this image, x multiplying lambda fx. Next, the period doubling renormalization operator T on P is defined by this equation. If F, TF, and etc. T and F belong to P, we denote gamma n sequence, and we have that T and F is equal to this, and lambda T and F is equal, it can be shown by this formula. Then let F 2K ordered analytic S unimodal map of the interval E into itself. It means that there is an analytic function H such that fx equals H x degree 2K, and F satisfies P1 and P5 conditions. That can be 5. That should be 5. For each K, there is a set of analytic functions WJK, for for map F, we have that T and F converges to universal function GK, which fixed point of T. That's this fixed point of this operator. And in Raphael Delavey, in their work, showed that these maps satisfies conditions of theorem 1 and theorem 2. Next, I formulate their result. Theorem 3. Let F belongs to this set for each K. Then, for any X belong to trajectory of 0 and P bigger than 2, the limit is 0. And let Cn be sequence of independent random variable which have P finite moments and satisfies A3P condition. Then there exists a constant gamma such that if sigma n satisfies this condition, for each x there are events bk, probability of bk goes 1, and omega n converge in distribution to the standard Gaussian. Then furthermore, there's a constant alpha and sigma depending on P, such that sigma n satisfies this equation inequality, analog of Bayesian inequality is whole.
Let me ask you the following question. This theorem is about linearized iterations. Am I right? This is not linear. This is not about true iterations. This is about some linear combinations with f prime. Yes.
No. This is.
Can you just again show us this Wn of x and sigma n, the formula for this? Yes, and what is x? X. This is. No, I see. Okay, so we just use this linearization for have right normalization. Yeah.
Yes.
This variance of ln.
Yes.
Okay. And also, let me ask you in this theorem 3 of these guys about Bayesian inequality, what can be the value of the alpha here?
I don't know, but it can be calculated. It can be calculated by computer, but I can't estimate. I can't estimate this value.
So they just say that they exist. Yeah.
Yes.
Okay.
Next. Next result for critical circle maps. Let T be an orientation preceding homomorphism of circle with the function f. F is continuous, strictly increasing, and fulfills this condition. The circle homomorphism is given T is then defined by this equality where mod 1 is fraction part of fx in x in 0, 1. Next, the Poincare rotation number of T defined as this limit. This limit is value of this limit is not depend on x, and rho T is called a rotation number. The rotation number rho T is irrational if only if T has no periodic points. Then rho T can be uniquely represented as continuous fraction as this, and we denote this right by this shape. Then denote by Pn Qn n's convergent fraction of rho T by K1 to Kn. This the number Qn denominator of P of this n's convergent number Qn are also called first return time of T and satisfies that recurrent relation with these initial conditions. Next, consider lift function f is analytic map such that E's derivative at the point 0 is equal 0 until 2k derivative, and 2k plus 1 derivative at the point 0 is non-zero. Denote critical circle homomorphism TF with lift function these and golden mean rotation number rho T is equal to square T 5 minus 1 2. If you represent continuous fraction, it's 1 1 1.
How do we know that such homomorphism exists, for which rho T will be equal to this value?
There is a lot of examples. We can construct this homomorphism with Arnold's map. It's fx theta fx rho is equal to sinus theta x plus rho. This homomorphisms are can be constructed easily.
Okay.
Then recall that the sequence Fibonacci numbers Qn is that, and there is a fact any integer n admits a unique Fibonacci decomposition by this way where M0 and MR satisfies this condition, and R the the number of term Rn satisfies this inequality. Next, there's beta is golden mean number. There's beta. Next, I formulate the fourth theorem of them already as explained in Abdurakhmon Aliyev. Let T be a critical cycle map if nk is increasing sequence of integers such that this limit is 0, then for all x trajectory of 0 and trajectory of 0 for all x and p bigger than 2, this limits is 10 to 0. This is first condition of two theorems, and let Xn as we say above sequence Xn sequence random independent variables that have p moments and satisfies A3p conditions. We have they exist gamma constants and sigma k. If sigma k satisfies this condition, for each x we have b and k, which probability goes to 1, and sigma and k converges in distribution standard Gaussian. Furthermore, if sigma and k satisfies this inequality, very analog Beres-Sein inequality is called. There is alpha is different from the third theorem. Alpha and theta different from third theorem. There's in other numbers. Next, results for cycle maps with a break. Natural extension of cycle homomorphisms, cycle diffeomorphisms are piecewise smooth homomorphism with breakpoints. We can see these homomorphisms, P homomorphism. The class of P homomorphisms consists of orientation preserving cycle homomorphisms T, which are differentiable except a finite or countable number of breakpoints xp, at which the one set positive derivatives exist which do not coincide, and for which there exist constants such that one side derivatives of breakpoints and also without breakpoints derivatives value is between these values, and logarithm of derivative of t has finite total variation in unit cycle. We see that kind of P homomorphisms. Then we extended theorem 1 and theorem 4. These homomorphisms homomorphism belongs to this set. Then I formulate our result with Jaliev. This theorem, let T belongs to this set and be cycle homomorphism with a breakpoint xp, just one breakpoint, and derivative of t strictly bigger than 0, and rotation number rho t can be represented this form. Consider the sequence independent random variables C n with p finite moments satisfies A3p condition for some x. X is belong to except inverse trajectory of this breakpoint. then there exists constant gamma such that if sigma n satisfy this condition, omega qn is for certain time, as I mentioned above, omega qn process converged in distribution standard Gaussian, and if sigma n satisfies these conditions, there is also holds Bayesian inequality. That's all. Thank you for your attention.
Excuse me, can I ask you about this theorem? What is the difference between the proof of this theorem and theorem which you mentioned before, when there are no such breakpoint?
First, they use to prove this theorem, and they use this theorem. They check conditions of theorem 1 and theorem 2 because of conditions are very complex. To check these conditions is very difficult. They use for them a renormalization technique. We use to prove this theorem another technique, which thermodynamic formalism. It's very different from their proof, and we also extended theorem 1 and theorem 2 by breakpoints cycle maps.
Also, can I add a little bit? So in that work, they studied circle maps, critical circle maps with a golden mean rotation number, and then here, in fact, they studied small perturbations, but after n steps, for xn bar, it is used the formula, Taylor's formula, and then in fact here this function ls, which is called Lyapunov function, which is linear part of Taylor expansion.
Yes,
so,
yes, it is, understandable. Yeah.
First, estimate this one, and the second nonlinear part is smaller. And then, but this idea was first used in Sinai, Wool-Sinai-Kayan's work for figure map also. But and that work they studied only when the support of the independent identically distributed psi n for this sequence, they studied the support of invariant measure if the support is very small. But here in that work they studied central limit theorem, but they here it is they support assumed that sigma n, the parameter, tends to 0 as n tends to infinity. And then they use it for, here main part is to estimate this the condition for a linear part. And then use it here the renormalization method, because for critical cycle maps and then for maps with break, they these things well studied. And but here in our work we studied such kind map with one break, and then for such kind of maps we're using the thermodynamic formalism.
What does it mean?
The same theorem. Huh?
What does it mean, thermodynamic formalism?
Thermodynamic formalism, this means we, for circle map with irrational rotation number, for example, in this case, with golden rotation number, using the, we consider the orbit of this point, of this singularity point. It is infinite because rotation number is irrational. Then using this orbit, we can construct the sequence of dynamical partitions. Dynamical partition, where we used only the orbit of this point, xb. And then using this this sequence of dynamical partitions, it is increasing partition. And then using these partitions, we can construct symbolic dynamics. This means for every x from circle, we can correspond.
Yes. Maybe I know another words, because in some of Sinai works it is called like in Russian перекладывание отрезков, interval interchanging. And after this, okay.
So we can pass to this space of sequences, and then on this space of sequence we will construct so-called in statistical mechanics potential for the map T. But this potential we will construct using the conventional probabilities, which we will use the ratios of intervals of this dynamical partition. So this is natural, by natural way they connected. So the lengths of the intervals of dynamic partitions we can express by this potential. So this is for circle dynamics, it is called constructing the thermodynamic formalism, because we can suppose that we will deal with infinite gas with potential energy U, and then we can construct here good statistical mechanics, because this potential is continuous function on Tikhonov topology, and the second, this potential weakly depends on if we consider the large particles with large numerous. It depends. It is almost a finite augment function. So such functions are good in statistical mechanics, and for such functions we can construct Gibbs measures and so on. But here, using this expression for intervals of dynamic partition by this potential, we can using the other things, so we can estimate this kind of Lyapunov functions. In fact, we can construct thermodynamic formalism if this map. For this map, we can study it is renormalization behavior. In these cases, we can construct thermodynamic formalism. But they use the renormalization method, renormalization behavior of the map. Here we use for such maps the thermodynamic formalism, and then we can estimate here these linear functions. So main part here to study the behavior of these Lyapunov functions.
Okay, very interesting.
In that work, they studied only the case if initial point X lies on the orbit of critical point. But here we can consider any point of the circle as initial point.
Very interesting. Let me ask you the following question. Did you study the joint behavior of different points starting from different orbits starting from different points simultaneously?
So you mean if we take 2 points, 2 different
exactly
points?
Exactly, two, three, or just consider all scaling limit for the random map which you get after n iterations.
No, your question we didn't study yet. Yeah, it is interesting question. You mean if we consider two orbits, what happens with?
Exactly. Because also here maybe some functional limit theorem can be formulated together with such a statement as your theorem 5. And then also it can be interesting to consider different starting points. Maybe you know, for us it is well-known work of James Norris and Turner, where they studied iterations of very simple mapping of interval 0, 1 to 0, 1, where we have just one jump with perturbed by one jump, and they consider the scaling limit and get a Arrhenius law.
Yes. No, this work we don't know. If you have send us, please. Okay.
Okay.
Maybe some coordinates of this work if you haven't.
Exactly. And actually, for me, this your talk was very interesting because I studied some sequence of iterations and with random perturbation. And the next question is following. You just get Gaussian limit for this normalized sequence. But what also about the right normalization in order to describe the set of partial limits of normalized sequence? Like you see the difference, we have central limit theorem and we have the law of iterated logarithm. Because you know, when you consider such random sequence, it will be interesting to study some frequency, how fast, how often this sequence visits some domains inside of the interval.
Yes, your question I understand. For example, we can study how long time the pure orbit will close to a random orbit. This one also we studied a little bit. But this question about entries time to interval, if I right understand your question, it is interesting question. It is very interesting question. Yes.
Okay,
you know,
so
these things we begin not a long time ago. We're only coming to this area. We studied more invariant measures, renormalizations, and so on for such circle maps with singularities. But this one is, in some sense, new one for us. Only we begin study, so we will be very happy to contact with you because.
Okay,
interesting for us if you did with such things. It is very interesting.
I will send to you some papers and maybe we can continue these discussions. But maybe some other participants of the seminar want to ask something or comment, please.
I have one question. So you use linearization and you have a few these bad points x, b, where the function is not differentiable. So do you estimate how often orbit is close to these bad points?
No. Yeah, we are taking when we estimate this Lyapunov function, we will estimate it except the orbit of this breakpoint, because here this function has no derivative.
Yes, I understand, but it is possible that the orbit is say x xk
xk
bad point and perturbed sequence is to the left of this bad point, and you cannot apply, say, Taylor formula.
In our consideration, we haven't such a technical problem, because when we use the Taylor's formula, we all time we suppose in our theorems x is not from orbit, because you know, if we consider for Qn, then it is enough for us to suppose that x not from inverse part of the orbit. For example, if we denote by x0, xb, then for x0, for x minus 1 till x minus Qn, if we consider this set, if x from not from this set, then everything is okay.
Well, maybe my question was as follows. Okay, assume that you are not in the orbit of these bad points.
Yes.
But it is possible that the sequence, this unperturbed and perturbed sequences are such that this bad point between them, then
you mean that the this stochastic orbit maybe will reach the breakpoint? Yes.
Not reach the breakpoint.
Yeah, it is possible also, because we are considering here small stochastic perturbations. We all time add the random variable. It is possible after a little bit moving the point, we can come to orbit of this breakpoint, and after some steps, maybe we will reach also xb. Here, no problem for us.
For example, assume that xb is 0. And
yes.
It is possible that unperturbed point is positive, but perturbed is negative. And you may have problems when you apply your linearization.
No, we haven't.
But Andrei, they control the intervals. Because if you this breakpoint breaks the initial interval onto two parts. After iteration, you have a lot of intervals, and they just follow the intervals. On each interval, they have, as I understood, more or less the same estimation for this Lyapunov numbers, and then you just control this infinite letters A, B, and so on, which describe your interval. Mm-hmm. Am I right?
And one more question about this golden mean. When you have 1, 1, 1 in the representation for rho t, is it possible to have another numbers of these ones are very important? From
just very nice.
Yes.
Just very nice.
You know, the renormalization transformation with rotation, if rotation number of algebraic type, this means rho has periodic expansion to continuous fraction. In this case, it is proved that the renormalization operator has periodic points. For these cases, we can construct thermodynamic formalism using this equation for periodic point or for fixed point. In other cases, in some sense, we can construct, but limit the Rx if this rho has periodic.
So you may have not once, but just periodic sequence.
Say it again.
I mean that rho t.
First,
not one, but periodic in this representation.
Yes, it is non-periodic, but beginning from m plus 1s, element, it is everywhere 1, 1. So the first elements, it is not difficult for us because we know this technique. It is not difficult. Because we can see the later dynamic partition after some m's renormalization will come, because after h renormalization we will the rotation number of renormalization will this one k1 if row beginning from k1, then after renormalization new map will has rotation number which beginning with k2. It is shift to the left one step. So after m steps, we will come to golden mean.
Okay, some more questions, comments? If there are no comments else, then thanks again to our speakers for interesting talk. And today we finish our work. Who will be the next speaker, Georgi?
Alexey Rudenko.
Okay, so see you next week. Bye.